All right, for stats 9.2, estimating a population mean, which is basically we'll be finding our confidence intervals and also required sample size to be so much confidence. All right, guys, so on our formula sheet, we are looking at, first off, that the sample size needs to be less than 5% of the population, and the data comes from a population that's either already normal or your sample size is greater than 30. So again, the sample size has got to be less than 5% of the population. That's one thing. The second, it comes from a normal population or you have more than 30. All right, if those conditions are met, two conditions, then you may proceed on to the confidence interval. And here is your formula. The degrees of freedom is meaning the number in the sample, -1. That's where you see an n-1 there. To get this t sub alpha divided by 2, and that's going to be inverse t. Instead of inverse norm, it will be inverse t. When you go to find the sample size, we'll be using this formula over here, and you'll notice it's back to the inverse z. It's a z sub alpha over 2 mil. Times S for the standard deviation. D capital E is the error, how much you're going to be within what for, like within how many, like 5 points or 6 points or 7 tomatoes or 23 for the blood pressure, whatever the numbers, but it's not a proportion. So it's not a percent, as these E's up here were all like, they all had to be between a 0 and a 1. So it might be like, I want to be 4% off or 5% off or whatever. Whereas this E can take on, it could even be 200. I want to be within 200. Okay. All right, let's go ahead and unshare and now reshare the homework. All right, so number one is going to have us just using the calculator to get the t values. So just practicing that first. Okay, so it says find the critical t value such that the area to the right in the right tail is 0.01. So this one's not a two-tailed one. So we're being told only this area on the right is 0.01. That means the area on the left then would be 0.99. So we're going to go ahead and go to our calculator, go invert second distribution, and y'all need to go inverse t. Okay, that's right below the inverse norm. So inverse t, the area is 0.99, the degrees of freedom. Now this is 22 degrees of freedom already. That meant that n was 23, and my degrees of freedom is 1 minus that, which is 22, df for degrees of freedom. So 22 degrees of freedom, and paste and enter, and that will give us our t. All right, so 2.5, how many decimals? 3, so 0.8. Next one again is another right tail. Okay, so the area to the right here is 0.025. We're already told the degrees of freedom is 13. So I'm going to do an inverse t. And now I'm actually going to just type 1 minus 0.025. Okay, it'll do that. 13 degrees of freedom, enter. And 3 decimals again, so 2.160. The area to the left is 0.25. So the area to the left here is the 25%. The degrees of freedom at 13. So second distribution, the inverse t at 0.25. So notice this time I did not do a 1 minus, y'all, because it was already the left area. So negative 0.694. And this last one wants find the critical t value that corresponds to 90% confidence, assuming 30 degrees of freedom. Y'all, so this time that's 90% confidence means this 90 is in the middle. So that's 10% split between the two tails. So this would be 10% divided by 2. Again, this is where I believe they should do plus minus, and they do not. So they're just going to want that positive on that. I really disagree with them. All right, so inverse t of 0.10 divided by 2. Again, 30 degrees of freedom this time, not 13. So 30 degrees of freedom. And again, just take the positive. It represents the plus and the minus. 697. The next number was a 2, so it would stay as 7. Okay, so the point estimate, that is the midpoint of they already gave you the confidence interval. See, they gave me, it's from 17 to 29. So the point estimate is the midpoint of those. That means I can take 17 plus 19, which is 36. 36 divided by 2, and that's going to be 18 for that point estimate. Whoa. Did I add them wrong? Yes, I did. 17 plus 29 is 46. Sorry about that, y'all. 46. I typed 19 there instead. 46 divided by 2 is going to be 23. Should have done it in my head instead of on the calculator. All right, that margin of error for the confidence interval is how far from 23 is it to each end? See, we got 23 to be the middle. So from 23 to 29 is 6 away, and that's also 6 away. So that's your margin of error of 6. So how far off of the middle are you? All right, a random sample size N is drawn from a population. The population we're being told is normally distributed. The sample mean X bar is found to be 109. Okay, so we know the X bar is 109. The sample standard deviation S is found to be 10. Construct the 95% confidence interval about the mean for a sample size of 20. Same question, sample size of 15. Then they're going to change the confidence interval, go back to sample size of 20. Okay, so you're going to go to confidence interval for a mean. See, this is about a mean, and we're doing confidence interval. So go to your formula sheet, go to confidence interval, about a mean. That formula says the confidence interval will equal your X bar plus or minus your T sub alpha over 2 times the standard deviation divided by the square root of n. So my X bar was 109 plus or minus. That first one wants to be 90% confident, 95, sorry. 95 is in the middle, so I need to take 0.05 divide by 2 for my inverse t. So we're going to do inverse t, 0.05 divided by 2. Degrees of freedom. Well, the sample size is 20. So if my sample size is 20, then my degrees of freedom is going to be 19. Okay, my inverse t is then 2.0930. Standard deviation was 10, the sample size was 20. So type the minus first, so 109 minus 2.0930 times 10 divided by the square root of 20. So, and they are going to one decimal place. So 104.3, comma. I'm going to up arrow onto the equation. I'm going to go back. I'm going to change that minus to a plus so I can get the upper bound, which is 113.68. Whoops, I wrote 133. I said 113. Okay, again, it was 0.68, so the 6 became a 7. All right, so let's go type this answer in. So 4.3, upper bound 113.7. Now, for my test, I don't need the formula written. Okay, I don't need this in the pink box written, but you must have this written, okay? And then your answer is typed in. Okay, so again, this must be written. Okay, that must be written now. All right, for part B, okay, the mean still stayed 109. This T is going to change, and my sample size changed. So this time, still 95% confidence, so still the 95 in the middle. Still need to take the 0.05 and divide that by 2. But this time, my sample size is 15. So my degrees of freedom would be 14, always 1 minus. So you're going to start with your inverse t. 0.05 divided by 2. Degrees of freedom is 14, 1 minus your n, or n minus 1. All right, so my t is 2.1448. So 109 minus 2.1448 times 10 divided by the square root of 15. Lower bound 103.5. Up arrow, back arrow to the minus and make that a plus. And that would become 114.5. I see how I got that symbol earlier. I thought I was pushing tab and I pushed the button above it. 5. How does decreasing the sample size affect the margin of error? So guys, when we make, so remember the margin of error is the distance from the sample mean to the end, okay? So if I'm thinking about 109, see 109 to here versus 109 to here. Which one's bigger? And the one with the smaller sample size. So how does decreasing the sample size affect that margin of error? The sample size decreases, the margin of error stayed the same. No, that margin of error increased. So now we're going to go back to the original sample size, okay, of 20, but it's the original sample size of 20, but now we're going to change the confidence interval. Okay. So middle, 80%. So we're going to take 20% divided by 2 to get that t. So again, that x bar was 109 plus or minus, let's get that t, second distribution, inverse t of 0.20 divided by 2. Degrees of freedom, since n is 20, my degrees of freedom will be 19. So that gives me my t of 1.3277. Standard deviation of 10 over the square root of n, which was 20. All right, so 109 minus 1.3277 times 10 divided by the square root of 20. Up arrow, change that minus sign to a plus sign. All right, first answer, 106. How many decimals? 1. So that stays 0. 2. 111.96. So that's going to become 112.0. Now, what happened this time? So from this first one, we were 95% confident. Remember, that meant if I take 95 different sample sizes of 20, then I'm going to actually capture the true mean. Okay, so here was that 95% confidence interval for size 20. And then here's 80% confidence interval for size 20. It's wider. Okay, it is wider. So, meaning as the level of confidence decreases, the size stayed the same. No, level of confidence decreased, the size of the interval decreased. No, my size of my interval increased. Okay, 1 second here. How's it worded? Let me read that wording again, guys. All right, let me clean this up. All right, how does decreasing the level of confidence affect the size of the margin of error? Oh, the margin of error was the distance from the 109 over, I am so sorry about that. Okay, so 109 to here versus from 109 to here. It definitely decreased it. Okay. So it decreased it as the confidence level decreased, the size of the interval also decreased. Okay. So how does decreasing the level of confidence affect the margin of error? The margin of error is that distance from the mean to each end. So I just take it from the mean to one of the two ends. Could we have computed the confidence intervals part A through C if the population had not been normally distributed? That answer would have been, let's see here. You would have to have a sample size of greater than 30 then. So because our sample size was originally normal, we could continue. So could we have computed it? No. That's because the population needs to be normal. Our random sample size of n, the sample mean is 17.9, standard deviation 4.1. Construct the 95% confidence interval for sample size of 35. So sample size 35 doesn't matter if my original was normal or not. Okay, so again, confidence interval. So y'all are going to go to x bar plus or minus the t sub alpha over 2 times the standard deviation over the square root of n. Again, you don't have to write out the formula with the letters, but you do have to write out this. So 17.9 plus or minus. Now we want 95% in the middle. That means to get that t sub alpha divided by 2, I need the 5% divided by 2 on an inverse t. So we're going to go to second distribution, inverse t, 5% divided by 2. N is 35, so my sample size, my degrees of freedom would be 34. All right, so we get a t of 2.0322, standard deviation 4.1, sample size 35. Okay, and then you up arrow under your formula. Y'all go change that to a plus sign. All right, so the lower first, 16.2 decimals this time, 49. And my upper, 19.308, so 31. All right, so part B, how's this changing? Oh, the sample size changed. Okay, so if the sample size changed, then I'm going to make this be 51. Okay, when I do my inverse t, my degrees of freedom will now be 50. And that means my t is now 2.0086. Up arrow, go back, changing that minus after the 17.9 to a plus. Okay. All right, so lower bound, 16.70. Upper bound, 19.05. Yes, stays at 5. How does increasing the sample size affect the margin of error? All right, y'all, so that margin of error is that distance from the sample mean of 17.9, okay, to the end, or 17.9 to this end. So as this went up, didn't the margin of error decrease? Right, so now we're going to do a 99% confidence interval for a sample size of 35. So again, it's confidence interval for a mean. So make sure you're always using those correct formulas. Confidence interval for a mu, which is a mean. All right, my x bar, 17.9 plus or minus. Guys, we're going to be 99% confident here to here. So I'm going to do an inverse t of 0.01 divided by 2. So inverse t of 0.01 divided by 2. Now, n is 35, so my degrees of freedom would be 34. So it gives me t's of 2.7284. Standard deviation was 4.1, square root of 35. Up arrow, change the minus to a plus, double check your numbers are typed right. Okay, so lower bound, 16.2 decimals, so 0.1, because it was 0.009. Okay, upper bound, 19.79, that is 0, so stay 7. Sure, it's going to ask about that margin of error and how does it affect this. All right, y'all, so that margin of error, again, is coming from the distance from the mean to the ends. So 17.9 to this end. 17.9 to this. Okay, so comparing the results from part A, how does the increasing level of confidence affect the size of the margin of error? So guys, from 17 point to 19.3, 17.9 to 19.7, so it made that margin of error larger. If the sample size is 18, what conditions must have been met? Then the original population would have to be normal. So the sample size must be large, and the sample should have no outliers. The sample data must come from a population that's normally distributed. It must come from a population that's normal, and the sample size be large. No, it's either normal or it has to be large. So all right, so now to the story problems. In a survey of 1,200 adults in a certain country were asked how many hours they worked in the previous week. Okay, so N is 1,200, y'all. Based on the results, a 95% confidence interval for the mean number of hours worked was, here's the lower bound, and there's the upper bound. Which of the following represents a reasonable interpretation of the result? Okay, so the confidence interval is 37.9 to 43.7, and this was a 95% confidence interval. Okay, so it says there is a 95% chance the mean number of hours worked by adults in the country in the previous week was between blank and blank. Let's look at these flawed. This interpretation makes an implication about individuals rather than the mean. The interpretation implies the mean is only for last week, and the interpretation implies the population mean varies rather than the interval. This is a test. Okay, so 95% chance the mean number of hours worked by the adults in this country in the previous week was between. I am going to go with correct. No. Flawed, because it's an implication about individuals. Interpretation plays the mean is only for last week. The population mean varies rather than the interval. That was a weird question, y'all. Okay. All right, so for number 5, part A, number 5, part A, you're going to go with flawed. The interpretation implies the population mean varies rather than the interval. The interval is going to move around because that's based off of the sample, but the population mean is going to stay the same. It's our confidence interval that's going to keep moving around. Right, we are 95% confident the mean number of hours worked by the adults in the country was between blank and blank. That sounds correct. "95% of adults in this country work between those many hours." Flawed. It makes an incomplete implication about individuals and not about the mean. Ooh, okay. All righty, and one more. We are 95% confident the mean number of hours worked by adults in a particular area of this country in the previous week was between blank and blank. I'm going to go with reasonable too. Not reasonable. Oh, okay. It's got to be the other flawed we didn't choose. Interpretation. Okay, so we've already done the implication. We already did about the mean. So it's going to be this one. The interpretation should be about the mean number of hours worked by adults in the country, not about adults. Oh, not about adults in the particular area. Okay, got it. All right, let's go back. Oh, I think if I go back and change it changes. Yeah, it does it all again. Okay. So when you guys are taking a look at that, Okay, again, on this last one, it says 95% confident the mean number of hours worked by the adults in a particular area. Back up at the beginning, it says 1,300 adults in a certain country were asked. It didn't say about anything about an area. All right, so D kind of really does make sense. A survey was asked 1,006 people. So N is 1,006. How many books they had read in the past year? So we have a sample mean of 14.2. We have a sample standard deviation of 16.6. And we want a 95% confidence interval for the mean. So confidence interval, mean. Number of books read. All right, y'all. So go to your formula sheet. It says confidence interval is X bar plus or minus T's of alpha over 2 times standard deviation, square root of N. Right, the X bar is 14.2. The T, we're going to be 95% confident. That meant the middle 95, y'all. So to get my T, I'm going to do inverse norm of 0.05 divided by 2. So in second distribution, not inverse norm, my bad. Inverse T of 0.05 divided by 2, degrees of freedom, N minus 1. N is 1,006, so 1,005. 1.9623 S 16.6 square root 1,006. Okay, the first answer is with the minus, the second answer is with the plus. And again, you can just up arrow, right? You guys can just pause the video. I'm not going to type it in. I'm going to go ahead and go to the next question. Oh, let's go back on that one too. Sorry, now my numbers were different, but in terms of which sentence to choose, you guys, there is a 95% confidence. Okay, not a 95% probability. Probabilities are automatically out. It says that. And if I repeat sample means are taken, 95% of them will have the sample mean between blank and blank. That is, but remember, we're about a confidence interval. So our sentence should be that I am 95% confident that the population mean of the number of books is between blank and blank. Okay, so that's the sentence we need to go with. So again, as I'm talking about these sentences for confidence interval, 95% confident, 99% confident, not 99% probability if repeated, okay? So know which sentence to grab first. All right, we need the point estimate. We have actual data values this time. So y'all are gonna go to L1 and you need to put these data values all into your L1. I need you to run a 1-bar stat because we're gonna need the X bar off of this data and we also need the sample standard deviation too, please. Says these data represents the pH of rain for random sample of 12 rain dates. We know N is 12. A normal probability plot suggests the data comes from a population that's normal, so we may proceed. The box plot indicates there was no outliers. Again, we may proceed. All right, so here we go. So again, go to Stat, go to Edit, go to L1, input all your data values. Double check that you've input them right when you're done inputting them. Right, then you're going to do a stat calculate, a 1-bar stat on L1, make sure that frequency list is clear. Okay, so my X mean, that's the point estimate, is your X bar. They said go to 2 decimal places, so 5.05. The standard deviation, they don't say how many decimals, we're going to go to 4. So 0.4017. First one's 95% confidence interval, the second one's a 99. So for the 95% confidence interval, we would have to do that 0.95 in the middle. We're going to do the point inverse T. So inverse T at 0.05 divided by 2 degrees of freedom, N minus 1, so it'd be 11 degrees of freedom. So the formula you'd have to put down in your test is going to be your X bar, 5.05 plus or minus that inverse t, 2.20, standard deviation 0.4017 over the n of 12. That's square root of 12, my bad. I hope on the last one I did square root. Okay, next one, the 99% confidence interval. So the only thing that's going to change now is, 99 is to get that t. So now to get my t, I got to do 1% divided by 2. So again, I'm going to do another inverse t, but I got to do 0.01 divided by 2 to get that one. Again, this mean is 5.05 plus or minus 3.1058, standard deviation 0.4017, square root of n, which is 12. Okay, and again, the degrees of freedom over here, degrees of freedom was 11. Okay, all right, y'all. So again, you type them in with a minus, you up arrow, you hit the plus again. So what I've done right here, y'all, this green is a minimum work to show. This is a minimum work to show. Now for part D. All right, what happens to the interval as the level of confidence is changed? So as the level of confidence increases, so it increased from part B to part C. Okay, then what happened? Let me clear everything off so we can kind of use our numbers here. So our mean was 505. So 505 to 530, that was an increase of 25. From 505 to 541, that's 0.36. So as my confidence level increases, okay, the level of confidence increases, the width of the interval increases. This makes sense that the margin of error increases as well. Because see, remember, this is the margin of error. So if that margin of error increases, then the confidence interval, the width of it increases as well. So meaning the larger the confidence interval, the larger the width of your confidence interval will be. The larger the margin of error as well. So again, we have data values. The company data represents the total tax in dollars, 3-day business in 8 random cities. A normal probability suggests it comes from a population that is normal. The box plot indicates no outliers, so we may proceed. All right, you'd put all those numbers into L1. You guys would run your 1-var stat. After you run your 1-var stat, again, this is your X bar right there. Okay, you would pick up your standard deviation as well, the S of X. You already have your N is 8. Again, to be 95% confident, you would do your inverse T up 0.05, cut in half, degrees of freedom of, since N is 8, 7. And then plug into your formula. Okay, and then it says the tax rate is between, no, we can't say it's definitely between. One can be blank percent confident that all cities, there is a blank probability, it's never probability. One can be 95% confident. See, so B and C both have that word confident, that the mean, see, this is a confidence interval about the mean. Okay, not the confident that the cities will have a travel tax between. It's that we have a mean travel tax for the cities between. And what would you recommend to researchers who want to increase the precision of the interval, but does not have access to additional data? So they would want to decrease their level of confidence then. Okay. Again, remember, if you decrease the level of confidence, it shortens your confidence interval, makes it more narrow if we want to narrow in. But if we want to expand it out, then we want a larger confidence interval. And honestly, if I put this one on the test, I'd probably tell you guys to go up and see. So I've not gotten there yet. I haven't made the test yet to make that final decision. Probably will. He wants to estimate the mean HDL cholesterol level for 20 to 29-year-old females. How many subjects are needed? That means find sample size. To be within 2 points, not 2%, within 2 points. 99% confidence interval, assuming S is 18.4 based on earlier studies. Suppose the doctor then wants to be he'll be content with a 90% confidence. So how large of a sample would he need then? So how does the decrease in confidence affect the sample size required? Okay. So we want sample size for mean. So go to your sheet, sample size for the mean is in parentheses, z sub alpha over 2 times the standard deviation over the error, how far off, squared, and again, round up. So 99% confidence, this is going to be inverse z, so inverse norm of, to be 99%, I need 0.01 divided by 2. Again, leave the 0, the 1. Okay, so for part, or I can't say part A, I'm just going to put 99%. So for the 99%, my z, 2.5758, the 2.5758, standard deviation of 18.4. The margin of error within 2 points, so that's my E. Whoops, I'm writing E instead of 2. You square it and you round up. Right, for the 90% confident, the Z is going to change. Everything else is going to stay the same. So now I'm going to do my inverse norm. So for 90% confident, I've got to do 10% divided by 2. So 0.10 divided by 2. This time my Z's are 1.6449. All right, you type in both of them, you round them up. Always round up. And they're even saying round up, round up. Right. So how does, if you decrease the confidence, well, it decreased the sample size. Y'all can see that right there. So decreasing the confidence, decrease the sample size needed. People are polled on how many books they read the previous year. Initial survey results. So we have a standard deviation of 11.5. How many subjects are needed? How many subjects are needed? That's confidence interval. Okay. We want to be within 4 books. This one's within 2 books. That's the E that's changing this time. So confidence interval for the mean. Okay, how many books? See, how many books? That's a mean, that's an average. It's not a proportion, y'all. All right, so we need to get that Z. So I'm going to first do my inverse norm. I'm 90% confident, 10% divided by 2. So I have a Z of, for part A, 1.6449, standard deviation 11.5, over the E of 4 in parentheses squared. Okay, and then again, round up. For part B, we're going to do second distribution. Again, another inverse norm, but still, oh, well, it's actually the same Z, still 90% confident. So for part B, the Z stayed the same. The standard deviation is the same. The margin of error within 2 books and squared. So again, this one was for A, this one is for B. That would be all the work you need to show. Round them up. How does doubling the required accuracy have, what effect does it have on it? Okay, on the sample size. So doubling the accuracy, it nearly quadrupled the sample size. Okay, it nearly quadrupled it, y'all, meaning times 4. Okay, so again, how does doubling the required accuracy, meaning you're going what effect does doubling the required accuracy have on the sample size? Doubling the required accuracy nearly quadruples the sample size. Then it says how many subjects are needed to estimate the mean number of books read the previous year within 4 books with a 99% confidence. Okay. don't like that they are so heavy, y'all, on like these parts right here. So I don't know, we might have to do a paper test on this one for this chapter. How many subjects are needed to estimate the mean number of books read with 4, within 4, so that's going to be your E. 99% confident. So again, we're talking mean. How many? That's sample size mean. So we need the Z. So Z is second. Inverse norm, second distribution. 99% 0.01 divided by 2 this time. And so my Z is 2.5758. Standard deviation, all the way back up at the beginning, 11.5. The E, how far off? 4, parentheses, squared. So this is for part D. And then again, round up. So compare this result to part A. How does increasing the level of confidence affect the sample size? Well, didn't it increase it, y'all? So increasing the level of confidence increased the sample size required. It did not decrease it. Then, so we know this one's out, did not decrease, and it did not decrease. Right? For a fixed margin of error, greater confidence can be achieved with a smaller sample size or a larger sample size. Okay, with a larger sample size, so for a fixed margin of error, so the fixed margin of error meant 4 for 4. Okay, the fixed margin of error, the greater confidence can be achieved with a larger sample size. So here's the larger sample size, and I have a greater confidence versus this was at 90% with a smaller sample size. All right, so just kind of follow along, like I said, for this part and this part here. So let me see, how would I word this if I do decide to put this on the test? I would probably tell you to just omit part C, so that would be an easy one to put in my teacher tip. But on part D, I would probably just say omit that down here as well. So you would just have to just pick the multiple choice parts. But I would want all these answers. So I could find some better questions. All right, your point estimate is your X bar, y'all. So the point estimate is X bar. You just put all those in L1, double check your datas are entered correctly. And you can run a 1-bar stat, make sure the frequency is left clear, nothing listed, and that's your point estimate. Okay, that next time. Oh, that was the last question. Okay. All right, y'all. We'll see you in class with your questions.